Hi students, welcome to today's lecture on artificial neural network. Till now in unit 5 we have discussed about the fundamentals of radial basis function neural network. We started with covers theorem, which is used in pattern separability problems, and then we have seen what is an interpolation problem and how the interpolation problem can be solved with the help of uh, the RBF neural network. Okay, so we started with those two topics, and then in our earlier class we have discussed about the architecture of RBF neural network, uh, which shows there is only one input layer, one hidden layer, and one output layer with exactly one output neuron when it is concerned with a binary classification problem. And for multi-class classification problem, there may be more output neurons in the output layer also, but we considered only the RBFNN with one output neuron in the output layer. Okay, and then we have gone through uh, an example problem for XR function, and we designed the RBF neural network for the XR function also in our earlier class. Okay, so let us continue the topic of RBF neural networks in Unit 5. Uh, in our today's class, we will discuss about the training algorithm used for RBFNN, which we already used it for designing the solution for XR problem in our previous session. Okay, so if any of you have not gone through that video, please watch that video first and then come back to this to understand how this training algorithm can be used in RBF neural network. Okay, right. So let us start how this training algorithm can be used for RBF neural networks. So let us again revise the basics of what is a RBF neural network and how we can use the function f of x to identify the output of an RBF neural network first, and then we will list out the steps used in RBF neural networks for training. Okay. So as I explained earlier, it contains RBF neural network contains three layers: input layer, hidden layer, and output layer with one output neuron. Assume that the inputs given to this input layer is x1, x2, x3, and the input neurons in the input layer is I1, I2, and so on, some IP. You can have any number of input neurons based on the size of input pattern given. And the hidden layer contains hidden neurons, and each hidden neuron will use a separate interpolation function phi1, phi2, and so on phi n based on how many neurons we have. Okay, so these are all used for calculating the interpolation matrix. Each hidden neuron makes use of a separate radial basis activation function with a different center. Okay, so we saw it in the example that we designed earlier also. And then if you observe, the hidden layer is connected to the output layer with the help of weights. Okay, whereas there is no weighted connection between input layer and the hidden layer. So if you can recollect, the conversion from input space to hidden space is done with a nonlinear mapping. Okay, that is the reason why there are no weights over here. And the conversion from hidden space to output space is done with linear mapping. Therefore, we require some weights here. Okay, so weights are connected only from the hidden layer to output layer only. And the final output from the output neuron of output layer let us say that it is f of x. So we need to derive a formula for this f of x, and how we arrive at this f of x. What are the steps used for calculating this f of x? Okay, so that forms our training algorithm, right? So this is a brief introduction to the RBF neural network, where it says neurons in the input layer corresponds to the input patterns submitted to the neural network. So the number of input neurons depends on the size of input pattern that we use, and each neuron in the hidden layer corresponds to the radial basis function centered on a point C. Okay, so every hidden neuron makes use of its own center, and you need to understand how these centers are calculated. There are some algorithms used for this calculation of centers, or else you can use some random centers also, just like we did it in our previous example XR problem. Okay, and the number of radial basis functions required depends on the number of hidden neurons used in the hidden layer. Okay, because every hidden neuron makes use of a different center, right? Then the output layer will have a weighted sum of outputs connected from the hidden layer. So that just we saw it in the diagram. So you can see it here. The output neuron is connected from the hidden neurons through some weights. So weighted sum is always there. Okay. So the final output from the output neuron can be treated as a weighted sum of outputs from hidden layer. That means the outputs from hidden space, let us say phi 1 of x, phi 2 of x, and so on, phi n of x, and the weights connecting to this output neuron w1, w2, and so on, wn. So I can define this output of output neuron as phi 1 into phi 1 of x into w1 plus phi 2 of x into w2 plus so on phi n of x into wn will become the output of this output. Okay, so we can now define this f of x. Okay, the output function of RBF neural network now can be described as f of x is equals to summation of j is equals to 1 to n, where this n is number of hidden neurons, wj into phi j of x. That's what I explained. Wj into, so what will be the formula here? Phi 1 of x into w1 plus phi 2 of x into w2, so on phi n of x into wn. So f of x can be defined like that. Okay. Now, uh, we know that these are the weights connected from hidden neurons to the output neuron. And what is this phi j of x and how we define this? Okay, so let us understand what is this. So in our earlier example, XR problem, we took an example phi of x, which is taken as Gaussian activation function, e power minus norm x minus c whole square, where c is the center that we select for the corresponding hidden neuron. Okay, so now in general, phi of x is going to be any Gaussian activation function that will be selected from one of these phi of x. So we have several options for selecting it. So you can select any of them based on your requirement. So this is a simple selection. Phi of x is equals to e power minus norm x minus c whole square, where x is the input pattern that we consider at that moment are submitted to the input layer of the corresponding RBF neural network, and c is the center that we select for a particular hidden neuron. Okay, so phi of x is equals to e power minus norm x minus c whole square. This is one possible option. Or the second option will be phi of x is equals to e power minus norm x minus c whole square by 2 into r square, where this r is going to be unit width of the corresponding RBF network. We will see how this R will be calculated in a a few minutes later. We'll see it in this algorithm itself, how this R will be selected and how the center will be selected and all. I will explain all these steps clearly. Okay, so this is another possible option for phi of x, or we can go with phi of x is equals to 1 by square root of x square plus c square. Okay, where x is the input vector and c is the center we select for the corresponding hidden neuron. Okay, so if you observe the Gaussian activation functions that we can select as phi of x for our hidden neurons, all these contains either C or R. Okay, so the performance of RBF neural network training algorithm mostly depend on how you select this C, that is center, or how do you select this R, and how the W is calculated. Okay, so the learning process of RBF neural network mostly basis on adjusting the three important network parameters. What are those three network parameters that we need to select? One is C, second one is R, and the third one is W. Okay. So based on how you select these three, C, R, and W, the performance of the learning process of RBF neural network will be uh, depends. Okay. Now let us see how these parameters, network parameters, can be identified. The first thing is, how do you identify the unit center C? So that is how centers will be selected. Uh, for doing this particular task, we can use any clustering algorithm to identify the corresponding RBF unit centers. The most preferred algorithm for this purpose is k-means clustering algorithm. Okay, so you can use k-means clustering algorithm to select centers for your RBF neural network. Okay, especially for the hidden neurons. Okay, so what it says, how this k-means clustering algorithm works. Let us go through the steps. The first step is initialize the center of each cluster to a randomly selected training pattern. So you can start with any input pattern as a center. Okay, so we'll select them randomly, and later we will check whether this random selection is performing well or not. Otherwise, you need to adjust the centers. Okay, now, so once we randomly select the centers, okay, the second step is assign each training pattern to the nearest cluster. Okay, assign each training pattern to the nearest cluster by calculating the Euclidean distance between the pattern and the center. That means after selecting a pattern as center, you need to calculate the Euclidean distance, that is square root of x1 minus x2 whole square plus y1 minus y2 whole square to calculate that Euclidean distance between 2 points by considering this cluster and all other remaining input patterns. Okay, so once you calculate that Euclidean distance between every input pattern and the center that is under selection, so what we do is, after calculating that distance, when all the input patterns are assigned to their clusters, then calculate the average position for each cluster center. So now all the input patterns are grouped into several clusters based on this Euclidean distance. Now, after that, what we are doing is input patterns, all the training patterns are assigned to their clusters. Calculate the average position for each cluster center. Okay, so we'll identify the average position for each cluster center. Now, based on this, we will identify the new cluster center, which is very close to this average position of cluster center that we identified in step 3. Okay, and this process will be repeated until the cluster centers do not change during subsequent iterations. So what is happening in this algorithm is we started with a random uh, pattern as the center, cluster center, and then we calculated Euclidean distance between every pattern to the corresponding cluster center that is identified randomly, and based on the distance we grouped them into several clusters. Okay, and when all the training patterns are assigned to their clusters, we'll calculate the average position for each cluster center, and once this average position is calculated, we will identify the new cluster center which is very nearer to this uh, average position. Okay, and we will repeat the process until cluster centers will not change in the subsequent iteration. So this is how we can calculate the centers for your RBF neural network, right? Okay, now let us see how the unit width R can be calculated for the RBF neural network. Okay, so this will be useful. This step will be useful only if you are using this phi of x is equals to e power minus x minus c whole square by 2r square as your radial basis activation function for the hidden neurons. Okay, for other activation functions, this step is not required. Okay, so let us see how this unit with r will be calculated. So when RBF centers are established, the width of RBF unit RJ, that is unit width of RBF unit RJ, can be calculated by using K nearest neighbors algorithm. Okay, so for identifying centers, we used K means clustering algorithm. Now for calculating the unit width RJ, we use K nearest neighbors algorithm. Okay, K nearest neighbors algorithm. Now, how this can be calculated? So let us imagine that the current cluster center is CJ. Okay, the current cluster center is CJ. Please remember this terminology properly. And then its unit width RJ can be calculated by using a formula. RJ is equals to square root of summation I is equals to 1 to K Cj minus Ci whole square by K. Okay, so this will be the formula to calculate the unit width. Rj is equals to square root of summation I is equals to 1 to K Cj minus Ci whole square by K. Now let us reveal what are these terms Cj and Ci. We know that Cj is the current cluster center, and with remaining centers we need to identify the difference between present cluster center with the remaining centers. Okay, and because it is the K nearest neighbors algorithm, the K value has to be chosen by the designer. Okay, generally the K value is going to be between 2 to n minus 1. Okay, the K value will be chosen between 2 to n minus 1. But the preferred value for K is always going to be 2. Okay, that means if you pick K as 2, it's going to be 2 nearest neighbors algorithm. That means we will see the 2 nearest cluster centers only. Okay, so this is going to be for I is equals to 1 to K Cj minus Ci whole square will pick among the 2 nearest neighbors when K is equals to 2. If you increase the K value, then it will pick the nearest K neighbors. The nearest K neighbors it will pick by the selected K value. And you need to perform a square root operation to find the unit width of the corresponding RBF unit. Okay, so that is how you can calculate the unit width RJ for a particular RBF unit. right? Okay, so now we have seen two things. One is how to calculate the cluster center, that is how to select the center C with the help of clustering algorithm. Okay, K means clustering algorithm, and uh, for calculating the unit width, the K nearest neighbors algorithm will be used. Now, the last parameter that affects the performance of RBF neural network is how do you calculate the width? Okay, so this we saw in our previous uh, interpolation problem also. So we mentioned how this weight vector would be calculated. Okay, so the first thing we need to do is because the input vectors are generally going to be in a low dimensional space, we need to convert that input space which is in low dimensional into high dimensional space. So how we did this in our previous example is uh, we calculated the interpolation matrix phi. Okay, the interpolation matrix phi for mapping the input vector into the output vector. So we know this, we did this in our previous example. So by performing this interpolation, by calculating this interpolation matrix, we can map the input space into hidden space. Okay, so this is what we did in our previous example. All right. Now, what we do is, our purpose is we want to find out the weight vector W. That means we want to calculate uh, the weights that connects the hidden space to output space. Okay, let us say we have this scenario where the weights are connected from hidden space to hidden layer to output layer. Okay, so let us imagine this is W1, this is W2, and this is W3. Okay, of course you can have some bias also. Okay, so I'm not assuming any bias here, you can go with the bias also. Now if you observe, the weight vector becomes a 1 by 3 matrix. Okay, 1 by 3 vector. Okay, or you can say 3 by 1 whole power transpose. Okay, right. So now, so what we did is we found this interpolation matrix that mapped the input space to hidden space. Now the hidden space is in high dimensional space, which can be linearly separable. Okay, now how do you calculate this weight vector W? So we know that the formula for weight vector is W is equals to phi inverse into D. Okay, when this can be used, if phi is a square matrix, then we can use this formula directly. Okay, so phi is the interpolation matrix, and assume that it is square matrix, then you can calculate the phi inverse. Okay, and then multiply it with the desired response vector. D is the desired response vector. So once you multiply this, you will get the weight vector W. Okay, so this is not always possible in a real-time scenario because the phi is generally not going to be a square matrix in every scenario, in every case. Okay, so if phi is not a square matrix, then we need to perform some inverse interpolation by using this formula. Okay, so in our previous XR example also, we performed this inverse interpolation to calculate the final weight vector. So how this inverse interpolation is done? First, we need to calculate the transpose of interpolation matrix and then multiply it with the original interpolation matrix. Okay, and for the result, we are going to apply this inverse. So we are going to find out the inverse for the corresponding result. Okay, so after calculating this inverse of 5 power t into 5, then again we will calculate, we will multiply the result with the transpose of interpolation matrix 5 power t. Okay, And finally, this is called inverse interpolation. And now we are ready to multiply this with the desired response. So why we actually do this inverse interpolation matrix is, if it is not a square matrix, then the number of columns in this matrix will not match with the number of rows of this desired vector. Okay, this desired response. So we perform a inverse interpolation to convert it into a matrix in such a way that the number of columns in the result maps with the number of rows of this desired vector. Okay, so that is what our purpose is. And this is the formula we use to calculate the weight vector when the interpolation matrix that is assumed is not a square matrix. Okay, if it is a square matrix, you can directly use this W is equals to phi inverse into D. Otherwise, you should use this W is equals to phi power T into phi inverse into phi power T inverse interpolation operation into D. That is the desired response. Okay, so uh, calculating this weight vector W is as simple as that, uh, which involves calculating the interpolation matrix phi. Uh, Calculation of interpolation matrix involves, we know, some radial basis function also. Please go through the previous XR example that I explained on earlier session. Okay, please go through that example first and then come back to this how to find this weight vector W. Then you will easily understand how it is done. Okay, right. So the performance of radial basis function neural network depends on three parameters that I said earlier. That is, one is choosing the centers. The second one is calculating that unit with R, and finally calculating the weight vector W. This also involves the selection of the radial basis function. It depends on radial basis function that we select also. So once we calculate these three properly, then the performance of radial basis function neural network will be uh, bettered. Okay, so you need to properly select these three steps, right? So that's all for today. So we discussed the training algorithm used for RBF neural network today. So let me briefly conclude what we discussed today. So we started with a simple architecture of RBF neural network with one input layer, one output layer, and one hidden layer, where the connections between input layer and hidden layer do not contain any weights, whereas the connections between hidden layer and output layer contains weights. And every hidden neuron uses a separate radial basis function for calculating, for mapping the input space into hidden space. Usually going to be, the conversion is going to be from lower dimensional space to higher dimensional space in general. Okay. And then we identified the function f of x that acts as the output value for the output neuron of RBF neural network. Okay, so f of x is equals to summation of j is equals to 1 to n wj into phi j of x. So that is the formula that we use to calculate the final value of f of x. Okay, and then the steps involved in training process of RBF neural network involves three things. That is based on, we have seen the options for phi of x also. Three options we mentioned. One is e power minus norm x minus xi whole square, that is c whole square. And the other one is the phi of x is equal to e power minus x minus c whole square by 2r square. Or the third option is phi of x is equal to 1 by square root of x square plus c square. Okay, so our final motto is to calculate f of x for training purpose. Therefore, it involves uses of any of these activation functions. So, which involves C and R as terms, and finally, the weights between hidden layer and output layer need to be calculated. Therefore, the learning process of RBF neural network mm, depends on how these C, R, and W are calculated. So for calculating the unit center C, we can use k-means clustering algorithm, which starts with selecting a random centers, and then we calculate the Euclidean distance between the selected centers and the remaining input patterns. And then after clustering, we calculate the average position for each cluster center, and we'll select the new centers which are close to these average positions later. Okay, so this process will be repeated until there will be no change in the center selected in the previous iteration. Then we saw how to calculate the unit width R using the formula Rj is equals to summation I is equals to 1 to k Cj minus Ci whole square by k, where k is the a random value that we select, which will be generally between 2 to n minus 1. And we call this algorithm as k nearest neighbors algorithm. Remember these two names. For calculating the centers, we use k-means clustering algorithm, and for calculating the unit width, we use k nearest neighbors algorithm. This is only useful only if you select an appropriate radial basis function. Okay. And finally, we saw how to calculate the weight vector W with the help of two formulas. When the interpolation matrix is square matrix, we have one formula. And if the interpolation matrix is not a square matrix, then we saw another formula that involves inverse interpolation. Okay, so that's all for today. In our next session, we'll be continuing the same concepts, radial basis function neural network, and we'll see the concept of generalization in radial basis function neural networks and how it is helpful in overcoming the problem of overfitting. Okay, so we'll see that in our next class. So that's all for today. Thank you all for your patient listening. See you in the next session. Thank you all.